Okay, so the next carboxylic acid derivative we're going to investigate are esters. And what I want to do first is review how to prepare or make esters. We saw earlier in this chapter that you can make esters fairly easily by starting with an acid halide. And if you have an acid halide, all you need to do is treat it with an alcohol and some sort of non-nucleophilic base like pyridine, and you can end up swapping out that chlorine for some sort of new alkoxy group. And that's important because this chlorine is such a good leaving group, it's pretty easy to displace with some other nucleophile. The other reagent we can use that's a little less reactive than acid halides are anhydrides. Same idea here. This entire group can be kicked off and displaced with an alcohol. So in this case, you can use some sort of alcohol. You normally don't even need pyridine in here, but it doesn't hurt to add in. And when you do that, you can again replace that leaving group with some sort of alkoxy group. In the previous chapter, we saw that we can convert a ketone all the way to an ester. But in this situation, we're not doing a substitution reaction, meaning there's no nucleophilic acyl substitution. Instead, we're going to do an oxidation reaction. Whoops, I forgot my oxygen in here. And in order to get this oxidation reaction to occur, we need to treat it with peroxy acid. So that's RCO3H. And if you remember, we have to be really careful. The oxygen can insert on that left side or the right side, depending on which R groups are attached in either position. Some alkyl groups migrate more readily than others, so we have to be very careful when we're identifying our products. All right, there's one last one that we saw, but this was a little while ago, all the way back in first term organic chemistry, and that was we can first treat a carboxylic acid with base, and by doing that, we can form this carboxylate salt, and this carboxylate salt is a weak nucleophile. And so what we can do in the next step is we can then treat this with some sort of alkyl halide, and we can do an SN2 style reaction, kick off that leaving group, and we can make an ester this way. The main thing to remember when you do this reaction is that this R group must be a methyl or primary, because we're doing an SN2 reaction, right? SN2 reactions won't work if that R group is sterically hindered. The backside attack just simply won't occur. All right, so these ones we've seen a handful of times before. However, we did want to cover a new reaction. And what I want to do is I want to compare and contrast it to the reaction shown above. And this is the Fischer Esterification. And in the Fischer Esterification, the whole idea is that you again start with a carboxylic acid, but instead of using base, what you're going to do is you're going to treat it with a catalytic acid, and I'm just going to call that H+. The reality is it could be sulfuric acid, tosylic acid, a wide variety of strong acids work here. And we're going to treat this again with our alcohol, and during this reaction, it's under equilibrium, but we can push it forward by removing water from the reaction mixture, kind of like we saw with our imine and enamine formation. All right, and when we do this, we can make an ester where our alcohol incorporates as that alkoxy group. So the question is, well, why would we do the Fischer esterification versus the method shown above? Well, the main reason is, first of all, the top reaction's 2 steps, and these alkyl halides tend to be really nasty reagents. They're bad for the environment and they're bad for human health. In fact, they're such good electrophiles that they can actually alkylate your DNA and cause cancer. So most chemists would prefer to avoid that method shown on the top and instead do the Fischer esterification. It's greener, it's faster, and it's a lot safer for the chemist and the environment. All right, so let's take a look at this Fischer esterification in a bit more detail, and we'll go over the full mechanism. And the mechanism is one that I showed in our lab. And in lab, we actually did this where we made a methyl ester. And so what we did is we first showed our carboxylic acid, and we used our strong acid. In this case, I'm going to show a one-way arrow because we know we're going to pull water out of the reaction and drive it out of equilibrium. And I'll put my alcohol down here. And the first step is to protonate our carbonyl. And when we do that, we make this into a much, much stronger electrophile because when we protonate this oxygen, we have a second resonance structure where that carbon has a full positive charge. And that means that that carbon underneath here with that positive charge is a very strong electrophile. So in the next step, our alcohol with its lone pair can really easily attack into that electrophilic center. All right, so when that happens, we're going to get a tetrahedral intermediate where we have two alcohols hanging off, and we've got this alcohol that was attached in, but it still has that proton on there. And so just like I did in the previous chapter, I'm going to kind of condense this down into one step, and I'm going to say, let's get rid of this proton and move it somewhere else. So I'm just going to write plus minus H plus and do two steps in one. And when we do this, we're going to move that proton over to one of these alcohols. It doesn't really matter which one, so I'll just put it down here. And we'll show our intermediate. Okay, at this point, we've got a really good leaving group down here. So this oxygen that's next to it can push its electrons down and kick off this leaving group. All right, and when we do that, we're almost done. However, we're not quite there yet. We now have this protonated ester and water that was kicked off as our leaving group. The last step that we need to do in this reaction is just simply to deprotonate our ester, to get to our final neutral product. So we can say we've got our ester and we've got water. I did want to make an important note, though, that I showed all of this as being in non-equilibrium conditions. The reality is it could be under equilibrium conditions if we're not removing water from the reaction mixture. So in fact, what I'm going to do is I'm going to go back and change all of these arrows to equilibrium arrows, just to emphasize the fact that it's really not a one-way reaction unless we're ensuring that water is removed from the reaction mixture. All right, so let's go ahead and fix these last few arrows, and then we'll make a few more reaction notes before we continue on. All right, so let's make a note here that the reaction is at equilibrium, but you can favor ester if you remove water. That's one method. So what I mean by that is in this reaction mechanism, what you can do is when this water is made, you can either distill it off and trap it, or you can absorb it into some sort of sorbent like molecular sieves. Molecular sieves have these little itty bitty pores that water can get absorbed into and trap the water that way. So by removing water, you use Le Chatelier's principle to push this reaction to completion. Or another method is just put in so much alcohol that it overwhelms the reverse reaction. So you use excess of your alcohol, and that's exactly what we did in lab. Rather than dealing with trying to remove and trap water, we just use excess alcohol. However, if you have the equipment set up, you can also do the method where you remove water. So this is called the Fischer Esterification reaction. It's a pretty common one. It's commercially used on fairly large scales, and it works well and is green. All right, so what I want to do next is I want to start looking at the reactions of esters. And there's a number of them, but we'll start out with the simplest ones. and these are the acid hydrolysis reactions. So really, this reaction is just like what we saw, but in reverse. So if you have an ester and you want to go to a carboxylic acid, all you do this time is you flood the reaction with water and then use catalytic acid. And what we'll do is we'll swap off this alkoxy group for an OH group. And by doing that, we'll make our carboxylic acid and we'll kick off our alcohol. So like I said, by flooding the reaction with water, you can actually push the reaction to the other side. So if you use excess water, then the ester is favored. Or sorry, the carboxylic acid is favored. And you can push the equilibrium over to the right-hand side. So that's one method. It's sometimes used, but not as commonly used as some other methods, like this next one. The next one is the base hydrolysis mechanism. And that's where you take some sort of ester, and with this ester, instead of treating it with acid, what you do is you treat it with hydroxide. This could be potassium hydroxide or sodium hydroxide. And in this reaction, the hydroxide is going to attack in. It's going to kick up electrons. Again, we're going to get a tetrahedral intermediate. And this time we're going to have a negative charge. It's okay to have a negative charge in this case because we're under basic conditions. And in the next step, we'll take this negative charge and kick off that alkoxy group. And we're not quite done yet. When we kick off that alkoxy group and form our carboxylic acid, the alkoxy group is such a strong base, it'll immediately grab the proton from our carboxylic acid, and instead of getting a neutral carboxylic acid, we're going to make a carboxylate where the oxygen has a negative charge, and then we'll have a neutral alcohol. This is also known as a saponification reaction. This is what we do when we make soap the traditional way. So with soap, what we do is we get some sort of plant-based ester, oftentimes a triglyceride. It can even work with animal-based esters. And then we treat it with lye, or some sort of hydroxide-based reagent. And then we end up making this carboxylate salt. The interesting thing with this is if this region of our carboxylate, the R group, is a long fatty tail, then that will dissolve the fatty oil. And then over here on this side, we've got a nice polar head group. This will be attracted to water, so you'll get a nice micelle forming where on the inside, all of those fatty tails are trapping your oil droplet, and on the outside of the sphere, you've got these polarized head groups, and you can trap and wash away oil that way. All right, so that's a really common way of hydrolyzing esters on a very large commercial scale. The next one is trans-esterification. This one's a little bit different, but the idea is still the same. So let's say we have an ester, and what we want to do is we want to swap out this OR group, the alkoxy group, for something new. Well, in order to do that, what we could do is use a huge amount of some second alcohol, and again, use acid. And if we do that, what we can do is we can, again, change out that alkoxy group and kick off our original one. It works best if you use this in an excess amount. So it works best if used in excess. It's essentially the same idea as the acid catalyzed hydrolysis that we saw up here. If you use excess water in that case, you favor your product. And down here, if you use excess alcohol, you can favor your product. All right, the next one is the same reaction done with amines. However, I would immediately caution you that this isn't very practical. It's really, really slow. So if you try to react an ester with some sort of amine, whether it's primary, secondary, or tertiary, this reaction where you would think you'd form an amide, it occurs, but at a glacial pace. It is very slow and impractical. So we show it here, but it's not something that's really useful synthetically. So we can pretty much ignore this in terms of synthesis. All right, the next one I want to look at is reduction. And we've actually seen this before. And with reduction of esters, we need to use a strong reducing agent, right? So in this case, the main reducing agent that we like to use as a strong reducing agent is lithium aluminum hydride. And if you try to do this, a lot of students are tempted to say, hey, if we do this, wouldn't we get an aldehyde? The reality is we cannot stop here, and we saw this in our previous term. So we cannot stop here with LAH. So what we do instead is we just use excess LAH, meaning more than one equivalent, and then in our second step, what we do is we treat this with water or some sort of weak acid in order to ensure that we get our alcohol out. So really, that is a problematic feature of using LAH, is we can't stop at the aldehyde. But as you saw in the acid halide chapter, there are workarounds to this, right? So in the acid halide chapter, we were actually able to stop at the aldehyde by using a bulky reducing agent. And that's exactly what we're going to do here. So let's take a look at our special bulky reducing agent. And this bulky reducing agent has these two big legs coming off of it, and then one hydride. If you remember from IUPAC naming, this entire group is called an isobutyl group. And so the name of this compound is diisobutyl aluminum hydride. It's kind of a mouthful, so instead what people call this is dibal. Or sometimes you see it as dibal H. I've seen it written a number of different ways, but it's just a lot easier to write out dibal than it is to write out the full reaction name. So this is our special bulky reducing agent that we use with esters. So let's see what this does if we treat it with our ester. So I'll show you an example here. If we have that same ester and we treat it with dibal, we can go all the way to our aldehyde and we don't run the risk of overshooting to our primary alcohol. Now, I remember a few years ago, students would ask me, well, why not just go all the way to this and then treat it with PCC to get to your aldehyde? Well, you could, but not only is that more steps, but PCC uses that chromium 6 based element or reagent, and because of that, it's really environmentally hazardous, and it's not something we want to use. It's been known to cause cancer if you get it in your body, so it's much, much, much better to use something like dibal instead, do it in one step, and avoid chromium 6 based compounds. All right, so let's take a look at the very last one. And the last one is what happens to an ester with a Grignard reagent. Well, this is one we've seen a number of times before, so this should be review. But the reality is, if you treat this with something like a Grignard reagent, some students will be tempted to show the ketone as an intermediate. But the problem with this is you cannot stop here. Instead, what will happen is it will overshoot and react with any unreacted Grignard reagent around, and you end up with an alkoxide, and if you protonate this at the end with some sort of weak acid, you'll end up with a tertiary alcohol. So the reality is we can't stop at the ketone coming from an ester regardless of what sort of reagents we use. I've had students ask me about the Gilman reagent, that lithium dialkyl cuprate, and the reality is I don't think it will react with esters very readily, so it's not something we would use in this situation. So really, to emphasize, if we want to go from here to here, instead of trying to stop at the ketone, we just use it in excess. I wrote magnesium twice, so RMgX in excess, followed by some sort of acid workup. Sometimes you just see water there, doesn't really matter. All right, so this is the full list of reagents that are used primarily in our textbook to react with esters. There are many, many more, but we're going to stop here, and when we come back, we'll take a look at our reaction map.